Okay, so let's get right into it. Inside every single device you own, your phone, your laptop, your car radio, there's a constant, invisible battle going on. It's this nonstop fight for clarity against an unseen enemy that's always trying to mess with the information we send and receive.
You know exactly what I'm talking about, right? That frustrating hiss when you're trying to find a radio station, or that crackle on a phone call that just drives you crazy. Well, that isn't just random bad luck. It's a real, physical thing, and it's basically the main character in our story today.
And here it is, our antagonist. In the world of communications, we call it noise. And really, it's any random, unwanted signal that gets mixed in with a signal we actually care about. You can think of it like graffiti on a masterpiece, or static in the middle of a symphony. The clearer we can make our information, the better we are at fighting this enemy.
So if you want to defeat an enemy, you've got to know it first, right? So let's meet the main culprits. These are the different types of noise that engineers have to battle against every single day.
First up is the most fundamental villain of them all, thermal noise. The best way to think about it is this. The tiny little particles called electrons inside every single wire, every component, they're constantly jiggling around because of heat. And that random vibration creates its own tiny, unpredictable electrical signal. It's a basic law of physics, sometimes called Johnson-Nyquist noise, and you just can't get away from it. It sets the absolute lowest limit for how weak a signal we can possibly detect.
All right, next on our list is shot noise. Now, what's really fascinating here is that this noise comes from the quantum nature of electricity itself. See, a current isn't a smooth-flowing river. It's more like a hailstorm of individual electrons. And the random arrival of these little particles, especially in things like transistors, creates this constant pitter-patter of noise.
And all this leads to a super important concept for engineers, white noise. Because things like thermal noise and shot noise are kind of spread out all over the place, we often just simplify things by modeling them as white noise. It's a great analogy, really. Just like white light is a mix of all the colors, white noise is a mix of all frequencies at the same power. And doing this just makes the math so much easier when you're trying to design systems that can fight back effectively.
So, we've met the villains. Now, let's see them in action. We're going to stage a classic showdown between two radio technologies you definitely know, AM and FM, to see which one has the better strategy for crushing noise.
Okay, so here's the heart of the battle. With AM radio, the music or the voice is encoded in the height, the amplitude of the radio wave. So the louder the sound, the taller the wave. But here's the problem. Noise is also an amplitude signal. It just adds itself directly to the wave, and your radio has no idea how to tell the difference between the music and the static. But with FM, the information is in the frequency of the wave, basically how fast it wiggles back and forth. And it turns out, noise has a really hard time changing that wiggling speed, which makes FM way more tough against interference right from the start.
And you know what? We can actually score this fight. Engineers use a thing called a figure of merit to measure how well a system handles noise. Think of it as a report card. A score below 1 means the system is actually making the noise problem worse, and that's AM. A score above 1 means the system is actively improving the signal quality, and that, my friends, is where FM really shines.
And this chart just makes it painfully obvious. AM's performance is, well, pretty terrible, with a typical score of around 1/3. FM, on the other hand, can get a score that's dozens of times better. It's not even a close fight. For that pure, high-fidelity, noise-free sound, FM is the undisputed champion, hands down.
But wait, because the story isn't over yet. FMM doesn't just win, it has a secret weapon that pushes its advantage even further into the stratosphere. Let's check out how this clever little trick builds on its natural strengths.
This is just absolutely brilliant engineering. Think about it. Those high-frequency sounds, like the S sound in speech or the crash of a cymbal, they're naturally weaker and much more likely to get drowned out by that hissing noise. So the transmitter intentionally boosts them before sending the signal out, making them stand out loud and clear from the background noise. Then your radio does the exact opposite. It cuts those same high frequencies right back down to their normal level. And when it does that, it slashes that annoying hiss that got mixed in along the way. It's a perfectly matched system.
So, just a fun story about old-school radio, right? Well, not exactly. This fundamental battle against noise isn't some relic of the past. It is happening right now, in all of our most advanced technology, and frankly, it's more important than it's ever been.
I mean, just look at this list. Every single one of these is a modern miracle that completely depends on winning this fight. The Wi-Fi connecting you to the internet right now, the GPS getting you home, even those incredible deep space probes sending back images from other planets. They all rely on super sophisticated techniques to pull a clear, meaningful signal out of the endless, unavoidable noise of the universe. Losing this battle means dropped calls, slow internet, a GPS that fails you in an emergency, or a crucial message from deep space being lost forever.
So the big takeaway here is that this is not a solved problem. As we push for more data, faster speeds, and rock-solid connections, we are constantly slamming up against the fundamental limits that noise sets for us. The next generation of engineers is going to have to invent even more clever ways to win this never-ending fight for clarity, and it makes you